So good afternoon, everyone. So this will be the third session with respect to the magnetism, right? For JEE means 2024 April session, right? So we'll be starting with the third session of this magnetism chapter, right? And with this session we'll be completing the third session of magnetism, right? Now let's begin with the question number one here. Two long and parallel wires are at a distance of 0.1 meter and a current of 5 ampere is flowing in each of these wires. The force per unit length due to these wires will be, right? So the question is that we have to find out the force between the two parallel wires, right? Through which the current of 5 ampere is flowing in each of these wires, right? The question is that two parallel wires, right? These are the two parallel wires. This is wire 1 and this is wire 2, right? These are the two parallel wires, right? And a current 5 ampere is flowing through each of these wires, right? And they're separated by a distance of 0.1 meter, right? 0.1 meter. We have to find the current force per unit length, right, due to these wires, right? We know that the parallel currents attract each other, right, and the anti-parallel currents repel each other, right? And the force per unit length because of the two currents. Let's suppose if I1 and I2 is the current flowing through the two wires, right? Then the force per unit length between them is nothing. It's mu naught times I1 I2 upon 2 pi times the distance, right? So this is the force per unit length between the two current carrying wires, right? If the two currents are parallel to each other, the force will be attractive, and if the two currents are anti-parallel to each other, the force will be repulsive in nature, right? So the force per unit length will be given as mu naught I1 I2 upon 2 pi t, right? This is the force per unit length, right? So let's calculate the force per unit length for this question, right? That will be F upon L will be mu naught times I1, I2, that will be 5 into 5, that will be 25, divided by 2 pi d. Now the distance between the separation between the two wires is given as 0.1, right? We can write it as it will be 25 upon pi, right? Multiplied by mu naught, that is 4 pi into 10 to the power minus 7, right? So from here, pi and pi will get cancelled. 4 into 25 will be 100, right? Or it will be 10 to the power minus 5, right? Newtons per meter, right? So this will be the force per unit length between the two wires, right? 10 to the power minus 5 newtons per meter will be the force per unit length between the two wires, right? Let's move on to the next question, right? The question number 2 is once again with respect to the force between the two current carrying wires, right? In this question number 2, three long straight wires, right, carrying currents are arranged according to figure, right? Three long current carrying wires are there, right? The current through A is 3 amperes and through B is 6 amperes and 8 amperes, right? And the separation between the two consecutive wires is given as 4 meters each, right? So we have to find the magnetic force on 20 centimeter part of the wire B, right? We have to find the magnetic force on 20 centimeter part of wire B, right? Now we know that parallel currents will attract and anti-parallel currents will repel, right? Force because of force on wire B because of this wire C will be attractive force, it will be towards wire C, and force because of wire A on wire B will be along this direction, right? It means the two forces will be opposite in direction, right? It means that the this will be the net force acting on this wire B, right? So let's calculate the force on wire B because of C and force on wire B because of wire A, right? So force per unit length because of wire C, right, will be actually equal to mu naught I1 I2, that will be 6 into 8 upon the distance between them, that will be 8 pi, right? That will be 8 pi, right? So 4 into 2 will be 8, it will be 8 pi. So from here 8 and 8 will get cancelled, we will be left with 6 mu naught upon pi, right? So this is the force per unit length because of wire C, right? But because of wire B, the same force per unit length will be because of wire A, that will be mu naught I1 is 6, I2 is 3 upon the distance, right? That's 2 pi times the 4, right? So from here, the distance will be actually 9 times mu naught upon 4 pi, right? So this will be the distance, right? So the net force between the net force acting on this wire B per unit length will be net force per unit length, right? That will be equal to 6 mu naught upon pi minus 9 mu naught upon 4 pi, right? Or we can write it as, so it will be 24, 15, right? It will be 15. 24 minus 9 will be actually 15 mu naught, right? 15 mu naught upon 4 pi. Right. So this is the net force, right? So from here, mu naught has the value equal to 4 pi into 10 to the power minus 7 upon 4 pi, right? So 4 pi and 4 pi will get cancelled. It will be 1.5 into 10 to the power minus 7 newtons per length, right? Per meter, right? 1.5 into 10 to the power minus 7 newtons per meter, right? But we have to find the net force on the 20 centimeter part. If force per unit length is 1.5 into 10 to the power minus 7, for 20 centimeter part, the net force on 20 centimeter part will be, we'll just multiply it with 0.2 meters, right? And 1.5 into 10 to the power minus 7, right? So it will be 0.2, it has to be equal to 3 into 10 to the power. So it is 1.5 10 to the power 6 here, right? Not 7. It will be 1.10 to the power minus 6, right? So it has to be minus 6 here, right? So it will be once again minus 7, right? But 3 into 10 to the power minus 7 newtons, right? So this much of force will be acting on the 20 centimeter part of wire B, right? So this is how we can apply the equations, right? The equation is that mu naught I1 I2 upon 2 pi t is the force per unit length between the two current carrying conductors, right? Magnetic force. Now, the question is that what is the net force on the square coil, right? We have to calculate the net force on this square coil because of this wire, right? Because of this wire, right? I can see here, let's denote this square coil with A, B, C, and T, right? A, B, C, and T, right? This is the square coil, right? So there are four sides of this square, right? On each of the on each side of the square, there will be a magnetic force acting on the each part of the square, right? And when we find out the net force, we'll be calculating the vector sum of all the four forces acting on the uh, four parts of the square to calculate the net force on the square coil, right? Now let's discuss. Let's discuss about this AB, right? AB, right? Now we can see here AB and CD are equal in length, right? They are 10 centimeter each, right? And they are at the same distance apart from this wire A, right? From this wire A. I can see here, if you find out the direction of the magnetic force on AB because of this wire A, right? The direction of the magnetic force on AB part AB will be, it will be given by DL cross B, right? DL cross B. The value of DL is along this direction, right? And the magnetic force, magnetic field is actually into the plane of this paper at this point, right? And perpendicular to it, right? It means that DL cross B has to be DL cross B has to be it will be along this direction, right? It will be along this direction, right? So on uh, AB, the force will be in the upward direction. Now talking about this part CD, since the direction of the DL vector is along this direction, then the force on this CD part will be in the downward direction, right? Now you can see here the length of each of these wires is 10 centimeter, 10 centimeter each, right? We know the force, it will be 10 centimeter on 10 centimeters the length of this AB part and 10 centimeters length of the CD part. So whatever be the magnitude of this portion of the force acting on AB, same will be the magnitude of this portion of the force acting on this part, but in opposite direction. It means that these two forces will cancel out each other, right? So these two forces, force on AB and force on CD, will not contribute to the net force acting on this coil, right? So let's talk about the portions CB and AD, right? CB and AD. Talking about the CB and AD. Now let's first talk about the AD. We know the force per unit length will be nothing. Force per unit length will be equal to mu naught I1 I2. That will be 2 into 1 upon 2 pi d. 2 pi times the distance. The distance here is 2 centimeter. We'll multiply it by 10 to the power minus 2, right? So this much of force will be per unit length, right? Length of this AD is actually 15 centimeter, right? We'll multiply here with mu naught 2 times 15. So it will be 15 into 10 to the power minus 2 upon 4 pi into 10 to the power minus 2, right? This and this will get cancelled, right? We'll be left with 2 and 2 will get cancelled. It will be 15 upon 2 pi times mu naught, right? Now let's talk about the directions. Since they are parallel currents, the force will be attractive, so it will be along this direction. So this is anti-parallel, the force will be repulsive, it will be along this direction. So force on BC, right? Force on BC will be nothing. It will be the length of BC, that's 15 centimeter, that's 15 into 10 to the power minus 2 times mu naught I1, I2. The current is 1 ampere, right? 2 into 1 upon 2 pi d. 2 pi d. Now the distance between them is from here to here it is 2 centimeter, and from here to here it's 10 centimeter, it is 12 centimeter, right? It has to be 12 centimeter, right? It will be 12 into 10 to the power minus 2. From here, this and this will get cancelled, right? 2 and 2 will get cancelled. So it will be 5 upon 4 into mu naught upon pi, right? So from here it will be equal to 5 upon 4 pi into 4 pi multiplied by 10 to the power minus 7. So this and this will get cancelled. We'll be left with 5 into 10 to the power minus 7 newtons, right? So this is the force on BC part, right? The force on AD was equal to, that was 15 upon 2 pi multiplied by mu naught has the value 4 pi into 10 to the power minus 7, right? So this and this will get cancelled, will be 2. So it will be 30. So we can write it as 3 into 10 to the power, or 30 into 10 to the power minus 7 newtons, right? Right? So the net force here will be F net on this loop will be nothing. It will be 30 into 10 to the power minus 7 minus 5 into 10 to the power minus 7, right? So that has to be equal to 25 into 10 to the power minus 7 newtons, right? So this will be the net force, right? This will be the net force acting on this current carrying loop, right? This will be the net force on the scare coil. Now let's talk about the question number. Let's talk about the question number 5, right? Now talking about the question number 5 of this session, right? A straight steel wire, a straight steel wire of length L, right, has a magnetic moment M. It is bent into various shapes shown in the figure. Find out new magnetic moment of each shape, right? Now let's suppose we have a straight wire, right? These are the two magnetic ends of this straight wire, right? Magnetic ends. Let's suppose this is the negative pole, this is the positive pole, right? The magnetic moment, magnetic dipole moment is nothing. It's M multiplied by the length between the two magnetic poles, right? So M multiplied by L, right? Now similarly here, let's suppose this is minus M, this is plus M, right? This is plus M. It's now bent into two and into this shape, right? So this pole, this will be the first negative pole of this magnet, right? And this will be the positive pole of this magnet, right? Now it has been bent in this shape, right? If this is L by 2, this is L by 2, then this has to be under root of, it has to be root 2 L by 2, right? Root 2 L by 2, right? That has to be equal to, that will be equal to L by root 2, right? L by root 2. So this will be the value of this length between, or the distance between the negative pole of this magnet and the positive pole of this magnet. The magnetic moment will be nothing. It will be the strength of the magnetic pole, right, multiplied by the length distance between the two poles, that will be L upon root 2, right? So this will be the new magnetic moment, right? Now for the same case here, right, if this is L by 2, this is L by 2, this is minus M and this is plus M, right? And this has to be L by 2, right? So the new magnetic moment will be here, that will be M L upon 2, right? So this is how we can find out the magnetic moments, right? So magnetic moment is nothing, it's the product of the magnetic pole strength, right, multiplied by the distance between the two poles of the magnet, right? Let's discuss this previous year question. A magnet of magnetic moment 50 ampere meter square, right? The magnetic moment of this object is given as 50 ampere meter square, and it's along x direction, positive x-axis, where magnetic field is given as 0.5 I cap plus 3 j cap Tesla, right? We have to find the torque on the magnet, right? Torque on the magnet, right? The torque on any magnetic material is nothing that's given by the magnetic moment cross producted with the magnetic field, right? So torque is nothing, it's given as M cross P, where P is the external magnetic field and M is the magnetic moment of the given material, right? Or given object, right? Now here for the given object, the magnetic moment has been given as magnetic moment vector has been given as 50 I cap, right? It's 50 I cap, and the magnetic field vector here is nothing that's 0.5 I cap plus 3j cap, right? So the torque on this magnetic object will be nothing. It will be M cross P, right? That will be 50 I cap crossed with zero point 0.5 I cap plus 3j cap, right? Now we can write this cross product in this fashion, right? So I cross I will be 0, right? I cross I will be 0, and I cross j will give us k cap, right? So it will be 150 k cap, right? 150 k cap. So this will be the net torque acting on this current carrying wire having magnetic moment along x direction, right? Now let's discuss a very important concept, that's the magnetic field because of the electron revolving in a circular orbit in an hydrogen atom, right? In a hydrogen atom or any other atom, right? So for this, we know that in case of as per Bohr's model of hydrogen atom, right? The electrons are revolving in the circular orbits, right? Electrons are revolving around the nucleus of an atom in circular orbits, right? With fixed energy, right? With fixed energy and with specific or fixed angular momentum, right? Now, for the same case here, we can see here when the electron revolves in this circular orbit, right? This circular orbit will behave as the current carrying loop, right? It will behave as the current carrying loop. And let's suppose the radius of the circular orbit is r, then the magnetic field at the center of this current carrying loop will be nothing. It will be mu naught I upon 2r, right? Mu naught I upon 2r. So magnetic field at the center or at the nucleus will be nothing. It will be equal to mu naught I upon 2r, right? Mu naught I upon 2r. Let's suppose the speed of this electron in this orbit is v, right? V is the speed. Then magnetic field at the center of this nucleus will be mu naught I upon 2r, right? Similarly, if we have to calculate this current I, it will be nothing. It's the charge upon the time, right? The charge here is the charge of electron, right? And the time is the time taken by this electron to complete a one revolution or one complete cycle, right? So the current will be E upon T, right? E upon T. It will be E upon T. Now talking about the time period will be nothing. It will be 2 pi R upon V, right? 2 pi R upon V. Substituting the value of time period here, it will be E upon 2 pi R multiplied by V. So it means that EV upon 2 pi R is the current because of this charge or because of this electron revolving in circular orbit, right? We can substitute this value to calculate the value of the magnetic field. It will be mu naught. The value of I is EV upon, so it will be 4 pi R square, right? 4 pi R square. So it will be, this will be the net magnetic field at the center, right? Uh, Effective current we have calculated. This is the effective current, right? This is the effective current, right? And magnetic moment. Talking about the magnetic moment, right? Magnetic moment is nothing. It's magnetic moment M is given as current multiplied by the area vector, right? The direction of the magnetic moment is actually the direction of the area vector, right? Let's suppose talking about the magnitude of this magnetic moment, it will be I into A. The current I here is EV upon 2 pi R, right? EV upon 2 pi R multiplied by multiplied by multiplied by the area, right? Area will be nothing, it will be pi r square, right? Now from here pi and pi will get cancelled, r and r will get cancelled, we'll be left with EVR upon 2, right? So this is the magnetic moment. So magnetic moment will depend upon the velocity of the electron, right? It will depend upon the radius of the electron, and velocity and radius in fact depends upon the principal quantum number, right? It depends upon the principal quantum number. For different principal n values of the quantum numbers, right? The value of the magnetic moment or the velocity and radius is different, right? According to Bohr's postulate, we know that L is nothing. It is equal to uh, nh upon 2 pi, right? Nh upon 2 pi. This is the angular momentum, right? Angular momentum. So Bohr's model says that angular momentum of an electron is quantized, right? Only integral value of h upon 2 pi angular momentum is possible, right? So L is angular momentum, right? It's a quantized angular momentum. And the magnetic moment we found it came out to be equal to magnetic moment EVR upon 2, right? EVR upon 2. This is the magnetic moment, right? Let's calculate the ratio between M by L, right? M by L. So it will be EVR upon 2 into NH multiplied by 2 pi, right? So from here 2 and 2 will get cancelled, right? 2 and 2 will get cancelled. So it has to be equal to, this is the angular momentum, right? Or it has to be equal to, we can write angular momentum as MVR also, right? We can write it as MVR, right? MVR also. So let's not calculate the magnetic moment in terms of the principal quantum number. We can calculate the magnetic momentum in terms of the velocity and radius of this circular orbit, right? So M by L, it will be EVR upon 2, right? Multiplied by MVR, right? Multiplied by MVR. So from here, VR and VR will get cancelled. Will be left with charge of electron upon the 2m, right? Now, in general, if the charge q is revolving in circular orbit, right? Charge q is revolving in a circular orbit, then m by l will have the ratio q upon 2m, right? And this ratio we call it as gyromagnetic ratio, right? It's nothing. It's the gyromagnetic ratio. It's a very important equation, right? It's used to calculate the magnetic moment because of the objects which is revolving with some angular velocity, right? Having some moment of inertia, right? This is nothing, it's called as gyromagnetic ratio, right? So it's a very important equation to remember. This equation is called as gyromagnetic ratio, right? Gyromagnetic ratio. Now let's suppose the ring is revolving right around the center, right? The real ring is rotating, right? It's rotating around its center with angular velocity omega, right? And the charge on this ring is actually a positive charge, right? It's a positively charged ring, right? It's a positively charged ring, right? Then the moment of inertia of this ring will be nothing about this axis. It will be, if the mass of the ring is m and the radius of this ring is r, the moment of inertia of this ring will be mr square, right? And the angular momentum of this ring will be nothing. It will be mr square omega, right? L is equal to I omega. This will be the angular momentum, right? If this is the angular momentum, right, then we can find the magnetic moment of this ring, right? The total charge on this ring is Q. The magnetic moment of this ring will be nothing. It will be Q upon 2m multiplied by the angular momentum L. That's mr square omega, right? Mr square omega. From here, m and m will get cancelled. So the angular momentum or the magnetic moment for this ring is QR square omega upon 2, right? So this is the net magnetic momentum of a ring, right? That is half q omega r square, right? Half q omega r square. This is the net magnetic moment of this ring. Similarly, if we have a disk, right? If we have a disk, right? Let's suppose this is the disk. Let's suppose this is the disk. And this disk is rotating about its central axis with angular velocity omega, right? Having radius r, mass m, right? Mass m, the charge on this disk is q. Now the moment of inertia of this disk about its central axis is mr square upon 2, right? We can find the magnetic moment using the gyromagnetic ratio. That magnetic moment will be L times L. The value of L here is mr square by 2 into omega, right? Mr square by 2 into omega multiplied by a charge q upon 2m, right? So from here m and m will get cancelled. So we'll be left with 1/4 of q omega r square, right? So this is the gyromagnetic ratio, or this is the magnetic moment of this disk revolving with angular velocity omega, right? So gyromagnetic ratio is a very important ratio used to calculate the magnetic moments, right? It's used to calculate the magnetic moments. Let's discuss this previous year question. The previous year question, this question was asked in the January session, right? The January is in the January session in one of the shifts, right? The question is that an electron moves in a uniform magnetic field, right? An electron moves with a uniform through a uniform magnetic field given as B naught I cap plus 2 B naught J cap Tesla, right? At a particular instant of time, the velocity of electron is given as this. If the magnetic force on electron is this much, right, where is the charge of electron, then the value of B naught is. We have to find the value of B naught. We know the total magnetic force is nothing, right? The total magnetic force The total magnetic force is given as that's nothing, that's QV cross B, right? QV cross B. This is the total magnetic force. QV cross B is the total magnetic force. Now the charge of this, it's electronic charge, that's electron E, V cross B, right? We'll write it as B naught I cap, right? Plus 2 B naught J cap. It's a cross product with, so sorry, this is the magnetic field, right? The velocity here is given as 3 I cap plus 5 J cap, right? Cross protected with the magnetic field, that's P naught I cap plus 2 P naught J cap, right? So we'll be once again using this cyclic unit vector system, right? That I cross I will be 0, right? I cross J will be K, right? So it will give us I cross I, it will be 0, and I cross J, it will be K cap, right? It will be 6 P naught K cap, right? And once again, J cross I will be minus K cap, right? J cross I will be minus K cap, it will be minus 5 P naught K cap, and J cross J will be 0, right? So from here it will be 6 P naught, right? 6 P naught E K cap, right? This is the net magnetic force, right? Now the question is that we have to find the value of this P naught, right? It's given as this force is actually equal to 5 times E uh, K cap, right? 5 times E K cap. So it means that from here 6 P naught has to be equal to 5, right? Means the value of P naught will be nothing. It has to be equal to 5 upon 6, right? 5 upon 6. So this will be the value of P naught, right? 5 upon 6 Tesla will be the value of P naught, right? So this is how we can calculate the value of P naught from the given condition, right? 5 upon 6 Tesla, right? Let's move on to the next similar question here, right? The next question is that the magnetic field at the center of a wire found by two semicircular wires R1 and R2, right? It's the situation is like this. Let's suppose this is the first semicircular wire, right? And this will be the next second semicircular wire, right? Like this. So this is the situation, right? And let's suppose its radius is R1, and this wire will have a radius of R2, right? Radius of R2, right? The R1 is given as the value of R1 is given as 2 pi m, right? The value of R1 is given as 2 pi meter, right? And R2 is given as 4 pi, right? 4 pi meter. The current flowing through the system is actually 4 amperes, right? And the magnetic field is given as at the center as alpha into 10 to the power minus 7 Tesla, right? We have to find the value of this alpha, right? Value of this alpha. We know that because of the semicircular wires, right? Because of the semicircular wires, we know the for any magnetic loop, right? Subtending an angle alpha, right? Its magnetic field is given as mu naught I alpha 4 pi r, right? 4 pi r, right? Now, since both are semicircular, here the value of alpha will be equal to pi, or we can write here the magnetic field will be equal to mu naught I upon 4 r. So this will be the magnetic field because of each of this wire, right? Now let's suppose the current, if this is the current, then because of this loop, the magnetic field here will be into the plane of this paper, right? And because of above loop also, it will be into the plane of this paper, right? So the net magnetic field will actually add up, right? So the net magnetic field will be nothing. It will be mu naught I upon 4, 1 upon R1 plus 1 upon R2, right? So this will be the net magnetic field, right? So value of I is given as 4 ampere, 4 and 4 will go. So we'll be left with mu naught 1 upon R1, that's given as 1 upon 2 pi plus 1 upon 4 pi, right? Or we can write it as mu naught times 3 upon 4 pi, right? 3 upon 4 pi. So the net magnetic field will be actually value of mu naught is nothing. It's 4 pi into 10 to the power minus 7, right? Into 3 upon 4 pi, right? So 4 pi and 4 pi will get cancelled. So 3 into 10 to the power minus 7 Tesla will be the net magnetic field, and the value of alpha from this equation is 3, right? So the value of alpha will be equal to 3. So 3 will be the value of alpha for this question, right? Now let's move on to the next question. A singly ionized magnesium atom is accelerated to kinetic energy given as 5 kilo electron volts and is projected perpendicularly into a magnetic field B of the magnetic of magnitude 0.5 Tesla. The radius of the path followed will be, right? We know the radius is nothing. It is given as mv upon qb, right? It's equal to mv upon qb, right? Now we can write this also as momentum upon qb, right? Now we can write momentum in terms of kinetic energy, that's under root of 2 mke upon qb, right? So this will be the radius, right? Now the kinetic energy is given as 5 kilo electron volts, right? 5 kilo electron volts. So it will be twice mass of electron, right? As it will be a mass of magnesium atom, right? It will be mass of magnesium atom. That is a single ionized magnesium atom. That's A is given as 24, right? 24. 24, it will be 24 atomic mass units, right? We can write it as 24 into 1.6 into 10 to the power minus 27 kg, right? So this much will be the mass of this atom, right? We can substitute the value of this, that will be 24 into 1.6 into 10 to the power minus 27. And the kinetic energy is given as 5 kilo electron volts, right? That will be 5 into 10 to the power 3, right? And electron volt is nothing, it's 1.6 into 10 to the power minus 19, right? So upon QB, right, the charge on this, since it's singly ionized, right, it will be 1.6 into 10 to the power minus 19, right? And the magnetic field is 0.5 Tesla. So evaluating this equation or this root or this calculation, we'll get to know about the radius of this path formed, right? Path followed by the singly ionized magnesium atom, right? So this is how we can do it. A beam of protons with speed 4. This is once again a question asked in the January session, right? A beam of protons with speed 4 into 10 to the power 5 meter per second enters a uniform magnetic field of 0.3 Tesla at an angle of 60 degree to the magnetic field. The pitch of the resulting helical path of proton is. And we also discussed in the last lectures also, the pitch only depends upon the pitch of the pitch of the helical path is actually nothing. It's actually the distance, horizontal distance traveled in one complete time period, right? That will be time multiplied by the horizontal component, right? That's a v cos theta, right? The pitch of the resulting helical path of protons is, right? So talking about the time period, that's nothing. That is time period is 2 pi m upon qb, right? That's the time period, right? So this is the time period, right? Now the time period will be 2 pi m. The value of m is given as 6 into 1.67 into 10 to the power minus 27, right? Upon that's charge. The charge of this electron is actually, the charge of proton is given as 1.69 into 10 to the power minus 20, right? Into the magnetic field, that's 0.3 Tesla, right? So from here we can actually calculate. Let's assume that this is almost equal, right? We can just cancel out this. So we'll be left with uh, 2 pi multiplied by, so it will be 10 to the power minus 8 here, right? Divided by 0.3. So this will be the time period, right? This will be the time period. The speed here is not given, right? Speed is given as say 4 into 10 to the power 5, right? So the time period pitch of this helical path will be time period, that's 20 pi into 10 to the power minus 8 upon 0.3, right? 0.3 multiplied by v cos theta, right? V is given as 4 into 10 to the power 5 cos of 60 degree, that will be 1 upon 2, right? So this and this will get cancelled, right? We'll be left with pitch of this helix as 4 pi into 10 to the power minus 3, right, divided by 0.3, right? So if we almost neglect this 0.3 and this can be written as 10. So almost we can approximate it to equal to, we can approximate it equal to 40 mm, right? We can approximate it equal to 40 mm. So 40 millimeter will be the pitch of this helix, right? 40 millimeters will be the pitch of this helix, right? So that's it for today, right? This was the fourth session, right? The third session for the magnetism, and we have completed all the important topics and all the important questions with respect to the magnetism, right? In the next lecture, we'll be starting with the electromagnetic induction and AC. That will be done started from tomorrow, right? So we'll stop here till then. Take care and goodbye.